Let's talk about complex numbers. When you were a child, you learned how to count the natural numbers like 1, 2, 3, 4, 5, and then you learned that there were no suckers in Grandpa's bag, or there was 0 of something. Those were the whole numbers. When you learned about the fact that you couldn't go outside with your new puppy because it was too cold, it was -6 degrees, then you were learning about integers, negative counting numbers. Then you learned about rational numbers when you learned about portions of pizza. I needed to eat 1/8 of a pizza if I have 1 slice out of 8, and I need a quarter from someone if I want to do a particular thing. So decimals and fractions are the rational numbers. Then somewhere around middle school, you learned about an irrational number called pi, and you learned about things like the square root of 2 or the square root of 17. And those are non-terminating, non-repeating numbers. Those are all part of the real number system. Then we ran into trouble because we wanted to be able to take square roots of negative things, and we can't do that because a positive times a positive is a positive, and a negative times a negative is a positive. So we needed something called I. And so the number like I, 3i, -7i are imaginary numbers. When we add those to the real number system, we get the complex number system. So I is defined as the square root of a -1. And the standard form of a complex number is a plus bi, where a is real and bi is the imaginary part. We always write the real part first, then the imaginary part second. So I allows us to solve equations like x squared plus 4 equals 0. What would be the problem with that? Well, if we say I want to get the x squared by itself, so I'll subtract 4 from both sides to create a 0 pair, and now x squared is a -4, and I want to reverse squaring, so I introduce a square root, and when I introduce a square root, I introduce the plus or minus, but suddenly I have to deal with a x is equal to plus or minus the square root of a -4. No number in our real number system times itself gets us a -4. So we defined I to be the square root of a -1, which means that x is now equal to plus or minus the square root of 4 times the square root of a -1, or 2, and the square root of a -1 is determined to be I. So our answers to this equation are plus or minus 2i. So it's helpful to understand how I works. If we take I times itself, I squared, we're taking the square root of a -1 times itself, and when we square a square root, their inverse operation, so our result is simply -1. If I want I cubed, I can take that -1 and I can multiply it by I again, and now I get -I. And if I want to get I to the 4th, I can take that -I and I can multiply it by another I, but a moment ago we said that I times I, or I squared, was a -1, and a negative times a -1 is going to get us a +1, and so it will cycle through. So if you want to know what is I to the 18th, well, that's the same thing as I to the 16th times I squared, and I to the 16th is 1, I squared is a -1, and so I to the 18th will be a -1. I to the 23rd is going to be the same thing as I to the 20th times I cubed. I to the 20th, the reason I chose 20 is because it's divisible by 4. That's going to be a 1, and then I to the 3rd, or I cubed, is a -I. So I to the 23rd is -I. So we can do lots of great operations with complex numbers. Adding and subtracting seems to be the most intuitive, because when we're adding, it's very similar to adding with variables. 6 is the real part, 1 is the real part, add real to real, and you get your real portion. -3i is your imaginary part, your 2i is an imaginary part, so we'll have a result of a -I. 7 minus I is the complex number. It's written as in a plus bi form. 7 minus 1i. Next, if we're subtracting, we have to remember that we're subtracting both the real and the imaginary part, so it may be easier to call this 5 minus I minus 2 plus 4i, distributing that negative to both. 5 minus 2 is 3, our real part. negative I, and a positive 4i is a positive 3i. A plus bi form, always real part first, imaginary part second. There's our complex number. To multiply, if we take a real portion times a real number times the complex number, we take the real times the real and get 24, and 2 times the negative 3i is going to get us a negative 6i. If we're multiplying a complex number times a complex number, we take our real times our real and get 8. Distributing our real times our complex, or real times our imaginary, we're going to get a positive 6i. Imaginary times real gets us a negative 4i, and imaginary times imaginary is going to get us a negative 3i squared. But a moment ago we said I squared was a negative 1. Negative 1 times negative 3 is a positive 3. And 8 plus 3 is going to get us 11. 6i minus 4i is going to get us a positive 2i. A plus bi form. Real parts always first, imaginary part second for our complex number. What if we're squaring a complex number? We have to remember that when we're squaring something, we're taking it times itself. So 2 plus 5i times 2 plus 5i, if we choose to use our product box to do this, is going to get us real times real, 4, real times imaginary, 2 times 5i gets us 10i, 5i times 2 is another 10i, 5i times 5i is a 25i squared. But 25i squared, I squared is a negative 1, so we'll get a negative 25 there. 4 minus 25 is a negative 21. And a 10i plus a 10i is a 20i. Likewise, we could have simply squared the first term. 2 squared is 4. Multiply the 2 together and double them, so plus 20i. Square the last, so 25i squared. 25i squared is a negative 25, plus 4 is a negative 21, plus 20i. We get the same result both ways. And finally, we're going to multiply the last two together. 3 times 3 is 9. 3 times 2i is going to get a 6i. Negative 2i times 3 is a negative 6i, and negative 2i times a positive 2i is a negative 4i squared. But I squared is a negative 1, so negative 1 times negative 4 is a positive 4. 4 and 9 is 13. And positive 6i and negative 6i are 0, is a 0 pair, is 0i. We don't have to write the rest. So this is neat because we've taken a complex number times a complex number, and we only have a real portion to that complex number. And we're going to use that when we're dividing by complex numbers. A plus bi and a minus bi, like the last example, are complex conjugates, and their product is a real number. So when we're trying to find the following quotients in standard form, we want them to be in a plus bi form, and that means that we do not want to have a radical in the denominator. Remember that 2 minus 3i is the same thing in the denominator as 2 minus 3 times the square root of a negative 1, and we like to do not leave the irrational numbers in the denominator. So to simplify this, we will multiply by its conjugate, 2 plus 3i. Same thing, just the opposite sign. Whatever we do to the denominator, we also have to do to the numerator so that we are multiplying by the number 1. So in the numerator, we will get 6 times 2, which is 12, 6 times 3i, which is 18i, I times 2i is 2i, so 20i total. And then I times 3i is a positive 3i squared, but I squared is a negative 1, so we have a minus 3. So in our numerator, we will have 12 minus 3, which is 9, plus 20i. In our denominator, 2 times 2 is 4. 2 times 3i is going to get a 6i. Negative 3i times 2 is a negative 6i. That's a 0 pair. No i's left. And negative 3i times a positive 3i is 9i squared with a negative out front. But negative 9i squared is the same as 9, a positive 9, and positive 9 and positive 4 is 13. So you can leave it in this form as far as I'm concerned, or if you want it to be in a true a plus bi form, you can also call this 9/13 plus 20/13 I. Letter B, let's do it again. In order to eliminate the complex number or the imaginary number in the denominator, we multiply our denominator by its conjugate, which is 4 minus 5i. Same thing in the numerator, 4 minus 5i, so we're really multiplying by 1. Numerator is going to get us 2 times 4, which is 8. 2 times a negative 5i is negative 10i. Negative I times 4 is a negative 4i, so negative 14i. And then negative I times a negative 5i is going to be a positive 5i squared, which is a negative 5. Denominator, 4 times 4 is 16. 4 times negative 5i is a negative 20i. 5i times 4 is a positive 20i. 0. And 5i times a negative 5i is a negative 25i squared, which is a positive 25. 8 minus 5 is 3. And we'll have a negative 14i in the numerator, and 16 and 25 is 41. So you can leave it in the first step, or we can call it 3 41st minus 14 41st I. Finally, we want to solve complex equations and our complex solutions of quadratic equations. So our first one is we're going to solve by square rooting. Because we have an x squared plus a 16x equals 0, there's no b term, there's no bx term. So if we subtract 16 from both sides, x squared is now equal to a negative 16 because of our 0 pair. When we introduce the square root, we introduce the plus or minus, and the square root of 16 is 4, the square root of a negative 1 is I. The second one requires that we try to solve in another manner. So when we have 3 terms, we can solve by factoring, and we can ask ourselves what are factors of 24 that could add to become 6. 24 times 1, 12 times 2, 8 times 3, 6 times 4 are the only integer factors of 24. So none of those will add to become a positive 6. So that means we need to either complete the square or solve using quadratic formula. If we're completing the square, we want to first start by isolating that constant. Take it to the other side by subtracting 24 from both sides. So x squared plus 6x will be equal to a negative 24. Then we ask ourselves what is the number that is going to give us a perfect square trinomial. And that perfect square trinomial comes from taking the half of the middle term and squaring it. So half of 6 is 3, 3 squared is 9. We don't have a leading coefficient, so we truly added 9. That means we need to add 9 to the other side as well to balance our equation out. Oops, sorry. Undo. Let's get back to that slide. All right, so we now have an x, meant to change my pen color, back to red. All right, we now have a perfect square trinomial that can be written as a binomial squared. X, sign of the middle, square root of the last, squared is equal to, and negative 24 plus 9 is a negative 15. Now we can add a square root to both sides. We're trying to isolate the x, and it's being squared. We do the opposite, square root, and we get an x plus 3 is equal to, we introduce the square root, so we introduce a plus or minus, and we can either put the I out in front or we can put it at the end, just making sure that it comes out of the radical. So I squared root of 15, or the square root of 15 times I. When we solve this, we're going to subtract 3 from both sides, and our answer is going to be x is equal to a negative 3 plus or minus I square roots of 15, or the square root of 15 times I. Had we decided to do this with the quadratic formula, we would say x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2 times a, which means that we are going to change the sign of b. So negative 6 plus or minus the square root of b squared, 36, minus 4 times 1 times 24, so minus 96, all over 2 times 1. And when we simplify, we'll have x is equal to negative 6 plus or minus the square root of 36 minus 96 is 60 all over 2. But 60 has a perfect square in it. If we divide 60 by 2, since it's even, we get a 30, and we divide 30 by 2, we get a 15, and 15 is 3 times 5. There are no perfect squares there. So this is as far as we can go, and we have a pair of 2's. The square root of 4 is 2. 15 stays inside. So we have a negative 6 plus or minus 2 square roots of 15 over 2. When we simplify that, it's like factoring a 2 out. So we'd have a negative 3 plus or minus the square root of 15 all over 2. Now that they're factors, we can cancel factors. We can't cancel sums or differences. And we get the same result that we had before. A negative 3 plus or minus I square root of 15, or square root of 15 times I. Apologies for losing that negative for a moment there. So you have an assignment. Bold and underlined are required. Others are highly encouraged. The more practice you do, the faster you are, the more confident you are, the better that you do on quizzes and tests because you have more time.